utility of the investor is the expected return of the investment minus 1/2 A sigma squared. Yep. So this is one specific way to describe investor preference. This is not the way to do it. It's actually one of the easiest ones that barely meets those criteria. So now that we know how to deal with investor preferences, we said, well, let's apply these and see how an investor would pick among different alternatives. So graphically, we have the expected returns of a portfolio, the risk, and if you have two portfolios that look like this, and portfolio of say X and Y, and you identify levels, combinations of risks and returns that produce the exact same level of happiness, those combinations of risks and returns will look like this. So those are all lines, all combinations of risks and returns that have the exact same level of utility. So from this we learn the higher up you go, the higher utility you get. And of course, the more you move in this direction, the lower levels of utility you get, right? So how do X and Y compare with each other in this case?
They have equal utility,
They have the same utility. Why?
because they are on the same indifference curve.
They are the same indifference curve, so investor is indifferent between X and Y. Yep. So if you throw in another asset Z, how would this asset behave?
Or relative, if you shift it over to the left to compare it to X and Y, you can see.
So one way to figure it out is, well, let me see the level of risk that Z has. Yeah, that's the level of risk. So if I take a portfolio that the investor is indifferent to compared to X and Y, this would be it. Let's call this XY. So this is a portfolio that produces the same utility as X and Y. And how does this XY compare to Z?
It's a higher return.
Same risk, higher return, so clearly XY is preferred to Z. If XY is preferred to Z and is the same of X and Z, then XY, they all prefer to Z. Yeah, I threw a couple of letters there that didn't belong when I just said it, but I can't spell. Alright, so we can say that both X, Y, XY, they are preferred to, it's like a greater than sign, but curly, means it's an indicator of preferences, is preferred to Z in this scenario. Yep. So what are we gonna have with this thing? Well, the idea is that, let's suppose that the investor can pick anything in here. So those are combinations. This set here contains possible expected returns and risk for a particular set of portfolios. Then can you tell me which portfolio would be preferred by the investor? So, like, can the investor pick Z? Why not?
It's not within the set of possible.
This is the set of what is possible, this is outside the set, so it's not possible, so Z is not possible. Now, if the investor could invest in it, maybe they would pick it, but it doesn't matter because that doesn't exist anyway. So Z is not possible. What about K?
Not possible.
It's not possible either. There is not such a thing with such a low level of risk, right? Risk decreases as you move to the left. So both Z and K, not possible. So anything that is possible is depicted by that potato thing. Yep, that's it. So how would investors select those investments? Well, overlap your indifference curves to this thing. And what would the investor prefer, X or Y?
Probably.
Well, X is close to this indifference curve, this is close to the one above, so it would look like that Y is preferred to X, right? Higher indifference curve. But is there a portfolio that is actually best, not just better than some? Is there one that is better of all?
Yes.
Well, if you were to draw this thing and find the point of tangency here, in this portfolio P is the only one that has the highest utility. How do you know that? Because it's on the highest indifference curve. So the investor in that particular case is better off with portfolio P. So this is the best portfolio. Yep. So if we know the characteristics of the investor, well, we have defined them pretty well through this utility thing. And somehow we have a way to figure out what that feasible set is, that we can merge the two things and identify that one unique portfolio that is absolutely the best. So then, last time we started working on, let's figure out what is the set of all possible combinations of risks and returns. So the way we did that, step 3, define the feasible set. And so what, in order to define the feasible set, things are complicated because it depends what kind of assets are mixed together. And let's start with the easiest possible way of combining assets. The easiest possible way, the first scenario. So, let me define it. So this depends on what you can invest in. Thank you, that was nice. So the first scenario, the easiest, assumes that you can invest only in risk-free and P. We call this the risky portfolio. This is the risk-free. And when you combine those two assets together, in some weights, you get a portfolio that we called the combined portfolio. So it's important that we agree on the notation here because otherwise things don't make much sense. So P is some risky portfolio, RF is the risk-free. When you combine those two, you get C. Yeah. So we started by looking at how can we combine P and RF? We said, well, by any proportion. So far we said that that proportion is defined as Y is the weight of P, which implies that 1 minus Y is the weight of F. Yep. So you can pick any percentage where Y, for the stuff we have done so far, we restricted Y to be between what number and what number?
0 and 1.
We said the most you can invest in P is 100%, so the most Y can take is a 1. What is the least you can invest in Y?
0.
0, you're just investing the other asset, right? So as a consequence, the 1 minus Y is also something that ranges between 0 and 1. So the two weights always add up to 1. Yep. Now looking at things going forward, that is not necessarily going to be the case every time. Y can actually take a value that is negative or bigger than 1, and that's if you're shorting. But we haven't discussed that yet. Remember, we're doing things in the easiest possible case that we can come up with. If things work, then we'll see, if we can make things more complicated. So then we said, well, if I mix P and RF, what levels of expected return is gonna get? So we said, well, if you mix them together, the expected return of that combination is equal to the weighted average of the expected returns. So you get Y ERP plus 1 minus Y risk-free. So depending on the weight, you're gonna get different levels of returns. At the same time, we said, well, what levels of risk of C can I get? And we said, well, the formula for risk of the combination was that the weight times the risk of one asset squared plus the weight of the other, risk of the other squared, plus twice the product of the weights, the product of the standard deviations times the correlation, but then that boiled down to just these. So from those things, we were able to extract two graphs. One that tells you what is the expected return of a combination given the weight of the two assets. So specifically the weight of the risky portfolio. So turns out that this is just a line, takes two extremes. One is if you invest nothing in the risky asset, you're investing only in the risk-free. So your combined portfolio is identical to just investing in the risk-free asset. So the return that you get is the return of the risk-free. Your entire portfolio is an exact match with that asset. On the opposite extreme, if you invest all in P, then your combined portfolio will have a return that is identical to that of P. So that's how the range of possible returns is depicted by that. Why am I putting ERP above RF?
Is the return, you would expect that riskier returns, or riskier.
So we are implicitly assuming that anything that is more risky than the risk rate will have a higher expected return, right? And so that's why it's like that. Then we did the same thing with risk. And we said, let's see how the risk of the combined portfolio varies with the blend I choose. So if you invest nothing in the risky assets, you're investing only in the risk-free. So if you invest in the risk-free asset only, then your risk is going to be, by definition, 0. On the other hand, if you invest nothing in the risk-free asset, but you invest only in the risky asset, then your risk is gonna be identical to that of the risky asset. So you have an exact match with that, so this is sigma p. And then we say, well, this is just a linear relationship, so those two must be connected with a straight line. Yeah? So for a specific level of a specific blend of P and RF, say 0.3, I picked 0.3 also last time, right? I always picked 0.3, I don't know why. You will have this return and this risk. For every weight that you pick, you will have a specific level of risk and a specific level of returns. Those two live together. They're all a function of the same parameter, they're all a function of weight. Do you agree with that? Yeah. So then the next thing was, well, we know how to invest in things. We know what are the constraints on what we can invest. Can we come up with a portfolio selection at this point? Well, graphically, we said, well, let's just combine to identify best or the optimal portfolio. We need to match the physical set and investor preferences. Yeah. So we need to overlap the constraints to the portfolio selection issue. So if you look at the investor preferences, those preferences are stated in terms of indifference curves. But those indifference curves exist in return risk space. You have return here, risk there. But what about this? But those graphs were obtained in terms of returns as a function of weight and risk as a function of weight. So how can we transform those two graphs in this frame, in this space? So we need to convert those two graphs where you have expected return of C as a function of Y and risk of C as a function of Y. You want to change them so that you end up with a graph that looks like this. This graph is expected return as a function of risk. So we need to take those two guys and change them into expected return of C as a function of the risk of C. So how do we do it? So if you remember from last time, we said, well, let's take those two functions together. And so to write those two functions in terms of Y as functions of each other, we said take the one that describes expected returns. Take the one that describes risk. They all have a common parameter. So these varies with Y, these varies with Y. So that means that if you change Y and you make this change, implicitly you make the other one change. So this allowed us to rewrite this thing as replace Y with this equation solved for Y, which is sigma C over sigma P, and you get this guy right here. ERC is equal to, what was it, crap, I need to do the math because I don't remember.
Oh, it's ERC.
ERC
Equals, the risk-free rate plus Y.
plus, so why we got rid of it, so it's gonna have to be
Sigma C over C.
ERP minus RF. Times sigma C over sigma P, is that right?
Mm-hmm.
Yeah. And the way we did all it was like this. So double check because I don't want to derive it again, it's kind of annoying. Here C is equal to F plus sigma C. Yep. Sigma P. Is that the way we wrote it at the end? The end of your notes from
Yes.
Monday? Yeah. So basically we said, oh, how does this thing look like? Well, remember we wanted to graph expected return of C as a function of sigma C. So I want this to be on my y-axis. This is on my x-axis. Those are the characteristics of the two assets and mixing together. So those are constants, they don't change. So this is fixed value. This whole thing is a fixed value. So I'm dealing with the equation of a line. Yeah. So you also know that if you invest 0 in P, then your portfolio is gonna have, your combined portfolio is gonna have a return that is equal to RF and a risk that is equal to 0. So if the weight is 0, you get this point. So you're just investing in, no, I like it. You're just investing in this. Ignore that. Yep. So you obtain that by investing only in the risk-free asset. The other extreme is that you invest only in the risky portfolio. So that means the weight of P is 1. That gives you an expected return equal to P and a risk equal to sigma P. So if you invest only in the risky portfolio, you get P, sigma P, you get this point right here. And then anything in between can be obtained by mixing these two linearly. That's it. So this is the equation of the line. You know the beginning point, you know the ending point, and you connect them straight. Yep. So then we said, let's try to make sense of this graph a little bit. How is this related to y? I mean, y is not depicted directly in the graph. It's indirect. So you achieve this point by using what level of y? You achieve this point by using what level of y?
0.
So to have a return equal to the risk-free rate, for my portfolio to have a return equal to just RF, the weight has to be 0. And if I have a weight of 0, what happens to my risk? Well, the risk associated with the weight of 0 is also 0. So this point corresponds to this level of returns and 0 risk. What if I invest only in P? So if I invest only in P, that means my weight is 1. This is my return with a weight of 1. This is my risk. So if I want to achieve this level of returns, I will have to be exposed to, this is another one, but this is sigma P. Okay. So the weight tells you what risk you will have given a particular level of returns. Alternatively, it gives you the level of returns for a given level of risk that you want to take. So this is obtained by having a weight of 0. This is obtained by having a weight of 1. So weight is not directly depicted in this graph, it's depicted indirectly. The higher the weight, the more you travel towards this point. Yep. Questions?
Just making sure that it is, but the top of the graph is supposed to be RC because it looks kind of like a 0 or a O.
This is RC.
Yeah, just making
Combined
sure.
portfolio, yeah, you're right.
Just kind of where I was looking from, it looked like
And
a.
it got,
Mm-hmm.
it was a very tired C, collapsed on itself. So, sorry.
No, I wanted to get my
No,
symbols
no,
right,
no,
so.
you're right. The subscripts, as I told you, are important, so. So once we got to this point last time, then what do we do?
Then you're in a different curve.
We said, okay, now I know what those are all the possible combinations of risks and returns. How can the investor pick one? Well, we overlapped the indifference curves graphically. And we said, hey, look, this is the combination, the point on the line that corresponds to the highest level of utility. So this is the optimal portfolio. And that's where we stopped, right? Do you agree with that? Questions? So let's move on a little bit. Let's see if this thing makes sense. Consider this scenario. And let's suppose that for a specific investor, the indifference curves look like that. So for a specific investor, that is the real portfolio. Kind of eyeballing it, how would you construct that portfolio? What weights? Give or take.
It's like close to 50%, maybe a little.
It's about halfway between the lowest return that you can get and the highest, so it's roughly 50-50. Invest half in the risky asset, half in T-bills. Now let's suppose, instead of dealing with this investor, you're dealing with one that is much more risk averse. So how would the selection change? For an investor that is more risk averse.
Should probably, the indifference curve should relatively shift left.
So hold on, let's think step by step. What does it mean that you're more risk averse?
You don't like it.
You're hurt by risk more than somebody who's less risk averse, right? So in general, if this is some level, average level of risk aversion, to maintain this guy equally happy as he is in this point, if you force this guy to take this much more risk, you need to reward them with that additional amount of returns. Do you agree with that? What about somebody who's hurt more by risk?
They would need a
To take the same amount of risk, will have to be compensated with more returns, right? So it's gonna require bigger compensation for doing something they doesn't wanna do. So in this case, somebody who's more risk averse will have indifference curves that are more curved. Do you agree with that? So let's see what happens if you draw these indifference curves kind of more curved. So this is gonna be the null point. Let's see if this makes sense with common sense. What is the characteristic of this portfolio compared to the green one?
Less risky.
Is less risky, but also has less returns, right?
Mhm.
And how do you construct it?
Be a higher A, or if you look at the
How do you get, how do you obtain a less risky portfolio?
more T-bills, higher proportion.
You are investing less in the risky assets or more in T-bills. So this portfolio, we said the first one, the green one was about 50-50 in composition. This one appears to be maybe, I don't know, 30-70, yeah, give it or take. 30 risky, 70% risk-free. And that is in line with common sense, right? Somebody who's more risk averse will be more comfortable investing more in less risky assets. So even though we did this stuff only graphically, the drawing itself is enough to logically arrive to a conclusion that is consistent with reality. So how can we do this mathematically though? How can we actually figure out how to construct the optimal portfolio? So finding the weights. To build the optimal portfolio. So let's figure out a way to compute it. So let's think about this. So how does the investor think? Well, the investor thinks in terms of utility. So recall that the utility of the investor will be equal to the expected return of the combined portfolio is going to end up with minus 1/2 A sigma C squared. You agree with that? So if you give the investor one particular combined portfolio, it will have a certain level of happiness. But how do we relate the expected return of the combined portfolio to weight? Well, we said the mathematical relationship was like this. We said here C was equal to, if you take this one and write it, you can write it as RF plus Y EFP minus RF. Remember that from last time, or 2 times ago? So this is it. This is just this formula right here, kind of rearranged a little bit. And we said that the risk of the combined portfolio is just Y sigma P. So this is how the combined portfolio is constructed, given that you can mix RF and P. So if U depends on this depends on Y, it follows that U depends on Y. Yeah. So we can write U as a function of Y. So just substitute and you get U is equal to RF plus Y EFP minus RRF. So this is the part that comes from the expected return of C. And then you have this minus 1/2 A. And then you have that sigma C squared, which is the same as this stuff right here. So it is Y sigma P squared, and this part is just sigma C. So I'm just substituting those two equations into that. Do you agree with that? Yeah. So I don't want to do much math here, besides just the one that is strictly necessary. But what kind of equation is this as a function of Y? So pretty much this is something that looks like this. This is a constant. This is a number times y. Then you have another number times y squared. Do you agree with that? So this is the equation of what? It's a polynomial. Specifically, starts with a P, ends with an A.
Binomials.
Parabola.
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 The binomial is just 2, that's 3.
This is the equation of a parabola. It's the u thing, right? Now the u can be either facing up or facing down. If the coefficient of the one with the square is negative, then this thing is facing down. Yeah?
So does that mean the curve of the parabola is going to form our indifference curve?
No, so this is just an assessment of how happy you are with each of those things. So every point will have, look at every point, if you travel along this line, which you will not be able to see anymore in a second. If you travel along this line, what happens? You're crossing a bunch of indifference curves,
Okay.
right? That means that your level of utility is changing as you travel this way. If you think about it, if you travel this way, what is happening to your utility? You're crossing indifference curves that are progressively lower, so your utility is going down. Suppose you travel the opposite direction, your utility starts going up. But then once you pass this point, what happens to your utility?
So it's going
It starts going down again. So your utility starts at some level, increases, reaches a max here, and then starts decreasing again, right? So this is coherent with something that starts at some point, reaches a max, and then drops. But if you graph this thing, well, it all depends what A is, but this is sigma C, and this is here C. You can calculate the utility at this point, and this point is obtained with the y of what? Y is 0, so you invest in the risk-free asset. So here the utility is equal to, if you plug 0 for y here, you just get RF. That's the value of utility. If instead you are at the other extreme, where you invest all in P, the level of utility, so here you invested all into this free, here you invested all in P, here the level of utility is this function right here, evaluated for y equal 1. And so if you put a y equals 1, because you are investing in P, if you put a 1 in here and you simplify that, you should get your P minus 1/2 A sigma P squared. That's how much utility you have. Okay, so the level of utility changes along that line. And those are all the possible combinations that you can get. So the question is, if I want to depict these as a function of y, how can I do it? Well, you can just pick points. If you have values, you can trace it. But we already know that the graph of utility as a function of derivative of this is my constant, the derivative of and is reduced to 1 unit. So cancel each. Why?
Explain how those three variables are.
Those are just the rate, the your forecast. So when you take the derivative of that, quantity yet. Then the 2 and the 1/2 cancel each other out. The math here, I mean, it should make sense and be for this particular. The outcome of who's 0.
A.
So with to invest. Split the money. And what size? The numbers in here. Yeah. That is great. So one, two, right? Okay.
Yes.
What does it mean?
Split.
Sorry. And that is the asset. Yeah. To arrive to the formula, get there. The reality is that you know calculus. utility. Three points. So you already know the peak, right? You want to know the highest point. So if y is 0, what are you investing in? You're investing only in T-bills. Is your level of utility is so at one point. The other point that would make sense is I'll use the formula for you. That's what you have there. What's the answer? Say again? For this particular scenario, or you can individually calculate sigma c and then plug them. So if y is point p plus y, this is not your p, this is yours. Minus Y is 0.5. Uh, 5.7%. Yep. What about what's the utility? 5 to but now those values are he's point.
Well, that's on.
Yep. So what are we here? On the what does the look like? Can you handle it? So um, way mixing those two things. But maintains that same level of utility. Think about all those graphs together. So you have some starting point, less risky. Lower weight of the risky asset means also less. You're making it better off from one point of view, but worse off from the other point of view. So the only function that puts everything together is that value of y. If you lower y, what happens? Utility goes down. Yeah. So it's impossible. What if this investor, instead of having an asset allocation that was half and half, it was invested with a y of 0.3, like the stuff that I have there. So if y is 0.3, this is his level of utility. You agree with that? And how could you make this investor happier
Increase the risk.
by increasing the weight of Y. Yeah, so that means create a portfolio that is more tilted towards the risky asset. Why is that making this investor happier? Well, yes, you're exposing this guy to more risk, but he's also getting more returns, and the trade-off, given his preferences, is such that he's better off. But then once you reach a certain point, taking on more risk is hurting him more than getting more returns, so his utility starts going down again. Yep. Questions? No? All right. So practice the quizzes, and then on Monday, we're gonna change things around a little bit, and we introduced, well, who says that Y has to be limited to 1? What if I can actually borrow? So if I can borrow some money and then invest in the risky asset, my Y goes above 1. So let's assume that you can invest in T-bills and the risky asset, but you could also short T-bills. Then what would happen to this thing? Well, the fact that you can invest more than 100% of what you have in the risk-free asset, that implies that your Y can exceed 1 if you are shorting. But remember, the weight of the two assets has to adapt to 1 all the time. So if this is bigger than 1, the other weight must be less than 1. I mean, the sum of the weights is, yeah, they have to adapt to 1. So if this is bigger than 1, that means that 1 minus Y, the weight of T-bills, must be less than 0. So this means that to indicate that you're shorting something, you would have to give it a negative weight. And so what do you think is gonna happen to this graph? Well, as of now, the graph ends when Y is 1. In this scenario, the graph will stretch past this point, okay? So what is the level of returns that you can get? What is the level of risk? What the level of returns is still given by the same formula. It's always the weighted average of the weights, except one weight is going to be bigger than 1 is gonna be negative. And ultimately, the net effect is that you still have a line, the equation of a line. You still have 2 points, so this line can only be extended outward. So there is gonna be a new limit. The new limit is gonna be whatever the most you can short will tell you what this thing is going to end. Okay, so this is the feasible set without borrowing. This is the feasible set allowing shorting and allowing borrowing. Yep. Questions? So how would that change that graph? Remember, Y is not going to be extended plus 1. So you're still using the same assets, same preferences. So if this thing gets extended this way, you might end up with some asset allocations for this particular guy that actually have a negative utility. Okay? So we'll work on that next time. If you don't have any questions, I'll see you on Monday. Start working on those quizzes and the